Welcome back. So this time I want to talk about what this term scalable means. We made the point that working with really large data is an important aspect of data science, and we've mentioned the word scalability before, but we haven't talked about really what that might mean. So a couple of different ways to think about it that I want to talk about here on this slide are here. So, operationally and in the past, one way to think about this was, look, it needs to work on data that doesn't fit in main memory on a single machine. Okay, so maybe you still only have one machine to work with, but this means that if it can, you need to be able to bring data off of disk in pieces, operate on it, and then maybe write it out in pieces. Okay, and so a bundle of algorithms that could work on data in this fashion by bringing in data piece by piece to memory, such that the memory footprint at any given point was small. This is something the databases provided. All right, so you could write a query, and you knew for sure that it was going to finish as long as the data was there on disk, and you had sort of a minimal amount of memory at least to get started. Okay, but and I might use the term out of core processing here. So out of core means it uses the disk to operate. So in core means everything you're doing fits entirely in main memory. Out of core means you need to sort of work with the disk appropriately. And so databases were the database community were specialists at out of core processing of large data sets. But increasingly, this notion of scalability wasn't really enough. Okay, and so you saw this pretty acutely with websites that were coming online in the 2000s, where one big server, no matter how big you bought that server, you couldn't bring data off of disk fast enough to meet all the requests, and so you had to start being sure that things were in memory, and the only way to do that is start adding more machines. Okay, and so increasingly, especially Google especially is sort of known for this, although many of the large media companies do this, is that scalable really kind of means being able to use up to thousands or maybe even more, tens of thousands of cheap computers and apply them all to the same problem. And so we might call this scale out, while getting bigger and bigger and bigger main memory and more cores perhaps would be scale up. Okay. Fine. So another way of looking at this that maybe is a little bit more precise is to think about this kind of in terms of algorithmic complexity that you may or may not be familiar with depending on how much computer science you've taken. But let me give you just a flavor of what's going on here. So in the past, you might call an algorithm scalable if given in data items, your algorithm does no more than n to the m operations on it. Okay. So this may be n may be 1, in which case it's a linear time algorithm, or it may be 2, in which case it's a quadratic time algorithm, and so on. But this was deemed, tractable, right? And so you'd prove properties about you would prove that you could find a polynomial time algorithm to solve some problem, and it was sort of thought to be scalable, or assumed, assumed. That was the definition of what scalable was. Things that were non-polynomial that took more than this, for example, exponential, where you might have m to the n, were exponential time algorithms, and they grew much, much faster, and they didn't scale. Okay, but this isn't a very tight bound on scalability in practice, right? A quadratic time algorithm may be sort of feasible. You start getting into the fourth and so forth, it becomes pretty difficult to do for very large data sets. Okay, so now you would say that it really can't just be n to the m, it's got to be n to the m over k, for some pretty large k. So you have to have a lot of k being the number of computers you can apply to the problem. And so you have to come up with an algorithm that can really exploit this properly. Okay. And then one more point that I'm going to make now, but we're not going to return to in this segment, but I hope to at the end of the course, is that it could be that soon even this isn't good enough. And for in data items, you really should do no more than in log n operations. And so the in here means for every data item that comes in over the wire. So this is applicable to sort of streaming applications. And the data is coming in so fast that you only get one pass at it. So for every operation I have, I'm allowed to process that data item, and then I'm allowed to put it in some sort of an index. And that's this log in factor. Okay. And so whenever you see log, you should think trees. So I'm allowed to take each item, inspect it, and work with it, and then stick it into some tree data structure. But that might be about it. It's just too big to make multiple passes at. Okay. And so examples of this might be this large synoptic survey telescope that we heard about. They're taking sort of 30 terabytes a night. You can't sort of make too many passes on this data at one time. Okay. And so this whole area we think of as streaming data, which I guess I have written here, but I'll write it again. And we'll come back to some of the techniques for dealing with big data in a streaming context. Okay, so fine. So two different views of what scalable might mean, and we're going to talk in this segment to give you some examples and some intuition for this. Can we make use of lots of computers and this in over K? Okay. All right, so here's a little example problem that's admittedly somewhat oversimplified. So we want to find all the matching DNA sequences where a set of sequences is a short string consisting of the letters G, A, T, and C, and you're given a short sequence, and you want to find all the ones that just exactly match that. Okay, so find me all the sequences that are exactly equal to this one that you're given. So how might you do this? Well, with this little cartoon, imagine that each one of these black lines is a sequence. Right, so this black line corresponds to this sequence, and this black line corresponds to this sequence, and all the other black lines are other sequences. And think to yourself for a minute, propose an algorithm to find sequences matching your target sequence. Okay. Well, making no assumptions about the data whatsoever, it's just given to you as a list. One thing you can do is do sort of a linear search. And so we're going to inspect the first item, and we're going to compare it to our target sequence. And if they're equal, great, we found one. And if they're not equal, what do we do? Well, we move on to the next one. So this is not equal, and this all happens at time equals 0. And then we move on to the next one. And so at time equals 1, we check another sequence and compare it for equality. And if it doesn't match, we keep moving on. And so on and so on until we get to time 17, where we find a match. And here I've said contains instead of equal. I guess I changed the meaning here. But so yes, we found a match and we send it to the output. Okay. So how long does this take? How many operations do we do? Well, we did 40 records. We were given 40 records in this cartoon, and we made 40 comparisons. And so within records and in comparisons, we say that the algorithmic complexity is order n. Okay, so this is a linear time algorithm for this simple search and retrieval task. So the question is, can we do any better? And if you've had some experience thinking about data structures, or taking some data structures classes, you should be thinking, yes, we can. All right. So one way to do this is to sort the sequences. So how does this help? Well, certainly we could still do the linear time algorithm and inspect these guys one at a time. But we can also do something a little bit smarter. What if we start in the middle? So start in the middle and compare our target sequence to the sequence we found here. And they're not equal. But we can see that this one that we found is less than our target sequence. Okay. So we know that the sequence we're on is to the left of our target sequence. We know the target sequence is to the right. Right? It must be somewhere in this direction. So we've just removed the need to check half of the data. Right? 20 records. Okay. So now jump to the middle of this guy and compare again. And now we see that, well, boy, we overshot. This one is greater than this one. Well, once again, let's see. Here we've removed half of these guys on the first step. And here we've removed half of these guys. And now we know it's in this range. Skip to the half again and compare this one, and now it's less than, so we're sort of bouncing back and forth around our target. Let's see if I can draw this a little better than I did. Cross those out. Cross those out. Now cross these out. And so we know it's somewhere on this side. And in the next step, we find a match. Okay. And here, if we have multiple copies of the same item, we know that they'll appear next to each other, so we could just walk through the records, gathering up all the ones that match if we needed to. Okay, so how long did this take? Well, here we still had 40 records, but we only made 4 comparisons, right? So within records, we made login comparisons. We navigated this sort of implicit binary tree. We did a binary search over this sorted data, okay? And so this lookup was order login. Now, we did have to sort the data ahead of time, and if you have to include that, then that's an in-login operation that we're not going to necessarily talk about. But once you have that sorted data available to you, it's now, it only takes login operations. And so this is perhaps far better scalability. All right. And this is a good trick, and it's such a good trick that it's been baked into many systems, especially, I'll argue, relational databases. And we made this point before, but I want to make it again, is that databases are good at these kinds of needle in the haystack problems, right? Extracting small results from big data sets. They can transparently provide this sort of old style of scalability. What I mean by old style scalability is that fits in main memory, as we've said a couple of times. Your query will always finish regardless of the size of your main memory. In addition, you can, it makes an excellent sort of index platform, a platform for building and using and reusing indexes, okay? So relational databases are good at this old style scalability in the sense of out-of-core algorithms, and they're also good at this old style scalability in the sense of finding logs, right? Finding logarithmic time algorithms, okay? So indexes are easily built and automatically used when appropriate. And we've talked a little bit about this during relational databases. You can write a single statement, create index, give it a name on a table and a column name, and it will sort records according to that column. Now, the actual data on disk may or may not be physically sorted depending on the details of which system you're using and how this is working. And typically in this statement, it would not actually be moving the physical records around, but it would build an auxiliary index. But regardless, you get to take advantage of this logarithmic time access pattern. Okay, and so just by writing this one statement in one line of code, you can create the index and take advantage of it. Okay, and then every query that comes afterward that needs to use that would benefit from using that index is able to. The optimizer automatically selects the correct index if it's appropriate to use. So this is much easier than you having to sort of rewrite your code by hand in order to either make it out of core, right, or to take advantage of an index. Okay, so when you're comparing relational databases to, say, scripts in R or scripts in Python, there's a lot of algorithmic work that's already been done for you that you're getting for free just by turning your problem into a SQL statement. Okay, fine. So you're, buying into a lot of code if you can tie one arm behind your back and write it as a SQL statement. It's not just SQL versus a much more expressive language like code. You're actually getting a lot of benefit out of doing so. Okay. So let's look at another task called read trimming. So here we're given the same set of DNA sequences, but instead of searching for one particular sequence, we're going to trim the final few base pairs from each sequence. Okay, so we're going to trim off a suffix and return the data set where each read is now just a prefix of a former read. Okay, so fine. So how do we do this? Oh, and the reason why you need to trim off the suffix, this actually comes up in practice, and the reason is that the accuracy of the sequencer drops off fairly abruptly after a certain length of read, and trimming off the last several base pairs from every single read is kind of a standard pre-processing operation. Okay. Fine. So how do we do this? Well, we can do the same trick that we tried the first time with the search task, meaning that we can process each record in turn one at a time. Right? So at time 0, we can trim off the suffix here and just return TACCT, and in time 1, we can trim off this suffix and so on. And at time 17, there's our old friend that begins with GATTA and so on. But here, unlike the search task, there's no index that's really going to help us, right? We have to touch every single record and manipulate it, right? We have to take a prefix from it and remove the suffix. And so the operation is fundamentally order in, right? There's not going to be an algorithm that is less than order in, right? You have to at least touch every single record. Okay, but can we do any better? Well, yeah, right? Processing the first task is completely independent from processing the last task, which is completely independent from processing this task. Well, I keep saying task, processing the record. Okay. So while there's no index, we can break this data set into pieces and process each piece independently. Okay. So imagine we take our single data set and break it into these chunks and assign each chunk to a different machine, or maybe a different processor to be a little bit more general. Now at time 0, we can process one sequence from each chunk all at the same time, and at time 1 we process the second sequence from each chunk all at the same time, and so on. And so here, how much work did we do? Well, we did the same amount of work. We still processed all 40 records, but how much time did it take? Well, it only took 7, I say cycles here, 7 time units to be a little more general, because we were given these 6 workers. And so the complexity here is n over k, right? For every item we can divide, we do on average, or for n items we do in over k time steps we're completed the work. Okay.